Great. So in the last video, we talked about how to represent theories as DAGs. And we made the claim that once you understand the DAG, once you understand the causal types and the nodal types, you're able to answer a vast range of queries. That's the claim we made. Okay. We're now going to talk through or try to show that that's right by talking through a set of different types of DAGs and showing the ranges of different causal questions you might want to ask and showing how those map onto nodal types and causal types. Here's the first one.
So, very simple DAG. We saw a DAG like this in the last video. We've got X pointing into Y, and we've got theta Y pointing into Y as well. That's going to represent how X affects Y. So, lots of questions we might have about a model like this, or even a simple model like this. Like, what would be what questions? What questions come to mind for you?
Well, the obvious question is you've got a case and you want to know, does X affect Y in this case? Sure. Case level causal question about the effect of X. That's my favorite.
We could also ask, like, does it affect Y? Or we could ask, does it have a positive effect on Y? Does it have a negative effect on Y? Or if we see a case where X equals 1 and Y equals 1, did X equals 1 cause Y equals 1? So that's slightly different, right?
Yeah, that's the attribution question. So that's sometimes called the causes of effects question. So given, as you said, given what we know happened, did it happen because of the cause?
Yeah.
Good question.
Yeah. And these are all questions about a case, right?
Right.
Now, one could also ask population level questions, right? Like, what is the average effect of X on Y?
Right.
Or for what proportion of cases in the population does X have a positive effect on Y, proportion of negative effect?
Exactly. So, and actually, in our world, in this world, the average effect of X and Y is equal to the share of cases versus the positive effect, less the share of cases versus the negative effect.
Right, that's right. And that works because we've got these binary variables, right? Okay, so let's take the query, does X have a positive effect on Y in this case? Right? So the key thing, and it's kind of a simple point, it kind of follows directly from everything we just said, is that is a question about the value of a node on this graph.
Right.
Specifically, it's a question about the value of theta Y. Right? Theta Y has these 4 types, and we've got some notation for that in the book. But essentially, we're asking, does theta Y take on the value, the type of value, in which X has a positive effect on Y?
Right. For which we're probably going to get at most a probabilistic answer. Maybe. Probably does, probably doesn't.
Right. We're gonna be learning about the likelihood that that's true. Yeah. Okay. How about this graph?
This is called a chain graph. So this is a graph where X might also affect Y, but if it does it does it through M. Right? X may have affected M and may have affected on Y. So what kind of queries might you have with this graph?
Well, I mean, of course, we might want to know about the effect of X on M. Right? Does X affect M? Does X have a positive effect on M? Does it have a negative effect? Right. So those are questions that are really questions about theta M. Right? What is the value of theta M? That's what represents X's effect on M. Similarly, M to Y. But we could also be asking here about what is the effect of X on Y, right? And we can map that onto nodes on this graph as well, right? So like we can ask a question about each step in this chain, but we can also ask, for this more complicated graph, what is the effect of X on Y? So how would we think about how that query is represented by or captured by node on this graph?
Okay, that's interesting. In the last graph, all the queries were queries by theta Y, right? If we understand theta Y here, we understand how M affects Y, but that's not enough to understand how X affects Y, right? Because we need to also know how X affected M. So that means the query, whether X affects Y, requires we learn about theta M and also about theta Y. We need to have information about a combination of those things.
Mm-hmm. One way to think about this, so or just to maybe go a little, sort of into a little more detail on that. So say we want to know if X has a positive effect on Y in this model, right? So there are really sort of 2 ways X could have a positive effect on Y. there could be a positive x to m effect and a positive m to y effect.
Right.
Or, so that'll generate a positive x to y, right? Or a negative x to m effect and a negative m to y effect, which, if you think about it, also generates a positive effect of x on y. And each of those two possibilities represent, are captured by two pairs of theta m, theta y values, right? There's the theta m value for which x has a positive effect on m, theta y value for m has a positive effect on y, and likewise for the two negative effects. And so when we're asking, does x have a positive effect on y? In this model, we're actually asking, do theta m and theta y take on either of those pairs of values, joint positive effects or joint negative effects?
Yeah, that's interesting. You can also imagine being pretty confident that x has an effect on y, right? And wondering, does it work through a positive effect of x on m and m on y, or is it through a negative effect of x, right? So that could lead you to queries of the form, I know x and y, right? Can I guess what m is likely to be, given what I know about x and y? It's another kind of question you can ask.
And in a way, that's also kind of a question. I mean, we're kind of getting already into questions about mechanism, right? Like, as you're saying, like knowing x has a positive effect on y doesn't tell us how. Right. And even though we know m has to be involved
here's kind of, that's right.
We know m has to be involved, but we may not know whether it's through a pair of, a sequence of positive effects or a sequence of negative effects.
That's right. Yeah.
And that is, as we're saying, a question about both theta m and theta y.
Yeah. Let's look at a slightly trickier one. Right. So this is a trickier one because in the previous one, if there were an effect, we have kind of assumed it runs through m, right? We haven't assumed.
Because we didn't have that x to y direct arrow.
That's right. Yeah, that's right. So what kind of queries can we ask of this model?
Well, of course, we could ask the same query, right? We could ask, does x, what is the effect of x on y?
Right. Yeah.
But we might also here wonder what pathway any such effect takes. Is it a direct effect?
Right.
Is it an indirect effect? Or what's the probability that it's a direct effect versus indirect effect? At the population level, we might want to know for what share of cases does x's effect on y run through m versus being a direct effect. So all those could be interesting questions here.
Yeah. Does the effect of x on y break down if m doesn't change? There's kind of a policy relevant question. But again, returning to the kind of the running point, all of those questions, lots of questions of that form, they all turn out to be questions about theta x, theta m, and theta y. Right? And in this case, most of them about combinations of theta m and theta y.
That's right. And just to sort of think that through a little further, like if we're asking, does x have an effect on y that runs through m? So to talk about it kind of loosely, like what we're really asking is, first of all, does x have an effect on m? Right? You got to have that. So that's a question about the value of theta m. And then we want to know whether that change in m that we get when we change x, so does that change in m itself produce a change in y? And we might sort of add to that, do you need that change in m to get the change in y? In other words, can it not run just directly from x to y?
Right, that's right.
And that is really, it's complicated to say in words, but it is, in a fairly straightforward sense, a question about the value of theta m, as we said, but also the value of theta y. There's a particular value of theta y in which that change in m that you get when you change x generates is required to get a change in y.
Right. And so it's also possible that x would affect a change in m, and m itself would affect a change in y under some circumstances, but not under the circumstances in which x produces a change in m. So that the direct effects of x on y are pushing against the effects it would have had through m. So so many possibilities, but remarkably all can be summarized by understanding theta x, theta m, and their distribution.
All right, let's take one further step. So up to now, we've been talking about queries that we can ask about specific cases, like did x cause y in this case, or did x have a positive effect on y in this case? But often, social scientists want to ask questions about populations, like what is the average effect of X on Y across some population of cases, or for what proportion of cases in the population does X have a positive effect on Y, for what proportion does it have a negative effect? Or we might be interested in pathways at the population level, like through what pathway does X most often have its effect on Y? Well, like case-level queries, population-level questions can also be expressed as questions about the values of unobserved nodes in a causal model. All right, so let's now look at a causal model that has the lambda nodes. Okay, so think back to our causal models video where we talked about lambda nodes, right? So as you might recall, lambda nodes capture the share of a population that is of a given nodal type, right? So the thetas, theta x here, theta m, theta y, are the type, the nodal type that a given case takes on, but the lambdas represent the proportion of cases in the population of each nodal type. So for instance, thinking about lambda m, for instance. Lambda m is a vector. It's a 4-element vector that captures the share of cases for which X has a positive effect on M, X has a negative effect on M, and then the share for which M is always 0 and X has no effect, and the share for which M is always 1 and X has no effect. Or we look at lambda y. So lambda y is itself a 4-element vector that's going to capture the share of cases for which M has each of these kinds of effects on y. A positive share with a positive effect, negative effect, no effect with y at 0, no effect with y at 1. Okay, so now the key point here is that just like case-level questions can be framed as questions about the theta values for the case, population-level questions can be framed as questions about the values of the lambda nodes, or elements of the lambda vectors in the causal model. Of course, the key thing is that both the thetas and the lambdas are themselves unobservable, but as we talk about in the next video, we can use data to draw inferences about theta and lambda and get at the questions that we're interested in.
And so that's sort of a big part of what the approach, an important step in the approach. It's also an important thing that the causal query software package does for us. Right. Once we specify our queries, it's going from what's the causal question that I have to what are the nodal types or causal types, the combinations of nodal types that satisfy that query.
Right. And what's the probability that we have those causal types in a given case or in a population?
And we're going to use data to figure that out.
Okay, that's the next video.